And good afternoon, everybody. Here are some notes and examples for the next section. It's going to be covering section 3.3 from our book. It's going to be on the cosine of a sum or difference. Essentially what we're going to be doing is we're going to be taking something that we typically cannot find an exact value for, so something that is not a special angle. So for example, cosine of 75 degrees. If we tried to find the exact value from our reference angles, 75 degrees. So if this was 75, we don't have a special triangle with a 75-degree angle in it. So our special angles are 30, 60, 90, 45, 45, 90. We don't have a special triangle memorized as a 75, 15-degree special triangle. So what we're going to do is we're going to take this 75 and break it up into special angles that we do have. So for example, we could say that 75 is the same thing as 45, which is one of our special angles, plus 30 degrees. And these two statements are identical. 45 plus the 30 degrees is 75. We now have special angles, and there's going to be a couple formulas that we're going to look at that will tell us how to evaluate a statement like this. So let's go ahead and look at these two formulas. So the first one is going to be the cosine of a sum. So when you rewrite your non-special angle as special angles as a sum, so if you're adding your special angles, so in our case it was the 30 and the 45 being added together. So if you're going to rewrite them as a sum, then it's going to be identical to or equal to cosine of whatever your alpha angle is. So you're going to have two angles. One's alpha, one's beta. For us, I believe we said 45 plus 30, so our alpha would be 45, and our beta would be 30. So you're going to just plug them into the formula, and it's going to be cosine alpha, cosine beta, minus sine alpha, sine beta. So finishing the problem that we started with cosine of 75. We said cosine of 75 is identical to cosine of 45 plus 30. And 45 will be the alpha, so we're going to say it's identical to cosine alpha. So cosine of 45 cosine of 30, cosine beta, minus sine of alpha, so sine of 45, and sine of beta. And the beta is the 30. And now we have something that we can find all the exact values for. So we basically just have four statements. We need to go through and evaluate each one. So kind of like what we did back in chapter 1, just 4 times over. So if we want cosine at 45, we need a picture for 45 degrees. And if it was 45 degrees, then we know that's going to be a 1, 1, radical 2. So the cosine ratio is x to r, so that's going to be 1 over radical 2. And if you rationalize that, that will be radical 2 over 2. So the first one, cosine at 45, will be radical 2 over 2. Times, we need the next one. The next one is cosine at 30, so we'll need a picture for 30 degrees. make some room here. So if we have a 30-degree angle, so what's across from the 30? That's going to be a 1, 2, radical 3. And what's our cosine ratio at 30 degrees? That's x to r, so radical 3 to 2. Minus, and then we'll do the next one, sine at 45. So the sine ratio at 45 is y to r, so that's 1 to radical 2, so radical 2 over 2. Times your sine ratio at 30 degrees, so look at your 30 degrees, and again, sine is y to r, so that's the 1 to 2. And then we can go ahead and simplify. So we have two fractions being multiplied minus two other fractions being multiplied. The minus sign is in the middle. So multiply your two fractions, multiply your tops and bottoms. Radical 2 times radical 3 should get you radical 6. Divided by 2 times 2 down bottom is 4. Minus, multiply your other two fractions, radical 2 times 1 is radical 2. Divided by 2 times 2 down bottom is 4. Subtract your fractions, you're going to need a common denominator, but we already have a common denominator of 4. So it's going to be square root of 6 minus square root of 2 all over 4. And this is the exact value for the original question, which is what is the cosine ratio at 75 degrees. So we took the 75 degrees, we broke it up into special angles. So we broke it up into special angles that make up 75 degrees, and then we use those special angles to find the exact value. One way to check this, if you have a calculator, you can check this on a calculator. So if you just put your calculator into degree mode and you get the decimal approximation for cosine at 75 degrees, and if you do that, you should, to 4 decimal places, you should get 0.2588. So if you evaluated this on a calculator, you should get 0.2588. And if you evaluated the left side, the square root of 6 minus square root of 2, just make sure you have that either in parentheses or you do it in multiple steps. But square root of 6 minus square root of 2, and then whatever you get there, divide it by 4, you should get the same thing. You should get 0.2588. So that would be a way to kind of check your work. So these would be the approximate values. This would be the exact value. The exact value is radical 6 minus radical 2 all over 4. And let's look at another example. The next example, same idea, except we're going to be working in radians instead of degrees. So you're just going to be needing to think of your special angles in radians. And we have evaluate cosine at pi over 12. And the other formula for cosine of a sum or difference is if you have to write your value as a difference, subtraction, then the formula is going to be a little bit different. It's still going to have the cosine alpha, cosine beta, sine alpha, sine beta pattern, but you're going to have a plus sign in the middle instead of a minus sign. But job one will be to rewrite our angle, pi over 12, that is in radians as special angles. And if you think about your special angles, to add or subtract fractions, you always need to have common denominators. And if you kind of think about your special angles, the first one is 30 degrees, which is pi over 6. The next one would be 45 degrees, which is pi over 4. And then the next one would be 60 degrees, which is pi over 3, and then 90 degrees, which is pi over 2. And as you kept kind of going through the quadrants, you would still be using the same special angles, just in different quadrants. So if you think about what the common denominator is between all of your special angles, what's common between a 6, 4, 3, and 2? That's going to have to be a common denominator of 12. So pi over 6 with a common denominator of 12. So they're all going to need a denominator of 12. And this is just so you can kind of combine them in different combinations to figure out which combination you need. So pi over 6, you've multiplied the bottom by 2, so this is going to be 2 pi over 12. So 2 pi over 12 is the same thing as pi over 6 with just a denominator of 12. The next one, pi over 4, you had to multiply the bottom by 3, so it's going to be 3 pi over 12. The next one, pi over 3, you had to multiply by 4, so it's 4 pi over 12. And multiply the bottom by 6 for the next one, so 6 pi over 12. So basically what this is telling us is if we're going to have a special angle, it's going to have to be some multiple of pi over 12. And then you can take that form where it's a denominator of 12 and find the correct combination. Not everything that is over 12 will be special. So for example, if you kind of kept going with this list, you have 2 pi over 12, 3 pi over 12, 4 pi over 12. Notice we skipped 5 pi over 12. 5 pi over 12, you can't simplify it down to something that's not a denominator of 12, so that is not one of our special angles. The next one on the list, after 6 pi over 12, if you kept going with the pattern, would be 7 pi over 12. But that is, again, not able to be simplified down to a denominator of 2, 3, 4, or 6. So that is not a special angle. That's not one of our memorized special angles. But the next one after 7 pi over 12 would be 8 pi over 12. So if you kept going even further and extended that list to 8 pi over 12, if you simplify this down, 4 goes into 8 twice, so you would get 2. And 4 goes into 12, 3, so you would get 2 pi over 3. And 2 pi over 3 is a special angle again. It's basically 2 multiples of pi over 3, or 2 multiples of 60 degrees, or essentially 120. So your special angles will always come in the form k pi over 12. And ones that can't be simplified down further are not going to end up being the special ones. So when you're dealing with radians, you're going to be wanting to think of your angles in radians. And let's go ahead and look at the problem that we had. So they wanted us to represent 1 pi over 12. So how can we get 1 pi over 12? We're going to have to use subtraction. And different students will pick different combinations. For example, 4 pi over 12 minus 3 pi over 12. 4 pi minus 3 pi, that would definitely get you 1 pi, so that would be one potential combination. Another combination could also work. For example, if you looked at 3 pi over 12 minus 2 pi over 12, that again is going to be 1 pi over 12. So you can pick different combinations as long as it is a correct combination. So let's go ahead and maybe use the 3 pi over 12. So we'll say this is going to be the same as cosine. And let's use the two smaller ones. 3 pi over 12 minus the 2 pi over 12. And once you figure out the correct combination, when it's in the k pi over 12 form, Then you can simplify it back to what you're kind of used to seeing it as. So what is 3 pi over 12 if we simplify that? So 3 goes into itself once, 3 goes into 12 4 times, so that's basically pi over 4, or a 45, 90, a 45 degree angle, minus 2 pi over 12 is pi over 6, so that is essentially our 30, 60, 90 triangle. And then go ahead and write the pattern. So if it's going to be a difference, we're going to follow this pattern. So it's going to be cosine alpha, where alpha is pi over 4. So cosine pi over 4, cosine of the beta, and the beta is pi over 6. And then if it's a cosine of a difference, we're going to have a plus sign in the middle. So it's going to be plus sine of alpha, so sine of pi over 4, and then sine of the beta, so sine of pi over 6, and then from here we just want to evaluate. So a cosine ratio at pi over 4, that is a 45, 45, 90, so it's going to be a radical 2 over 2, times the cosine ratio at pi over 6, that is a 1 radical 3, 2, and that your x to r ratio is going to be radical 3 over 2. Plus sine ratio at 45 degrees, or pi over 4, is radical 2 over 2. And the sine ratio at pi over 6, or 30 degrees, is y to r, that's going to be 1 to 2. And then go ahead and finish, multiply your two fractions, so radical 2 times radical 3 is radical 6. All over the bottoms, 2 times 2 is 4, plus, multiply your other two fractions, radical 2 times 1 is radical 2, all over 2 times 2, which is 4, so we have a common denominator of 4. So put your numerators together, radical 6 plus radical 2, all over common denominator 4. And that is our exact value for cosine at pi over 12. Again, you can check this on a calculator. Just make sure when you put it into a calculator, make sure you're in radian mode. Do cosine of pi over 12 when you're in radian mode, and look at the decimal approximation. And if you were to do that, if you type in cosine pi over 12 into the calculator, you should get a decimal approximation of about 0.9659. And if you compare this number to this number, those should be the same. So square root of 6 plus square root of 2, all divided by 4, is also 0.9659. And let's look at the next example. So this one is just using the pattern the other way. So they're giving us the cosine alpha, cosine beta, plus sine alpha, sine beta pattern. So if we see that pattern, so this is cosine alpha, cosine beta, plus sine alpha, so notice it's plus. That's going to help us decide which one to use. Plus sine alpha, sine beta. So if it's following this pattern, and if you have a plus in the middle, you want to match it up with the correct formula. So if you go back and look at your two possible formulas, notice the one with the plus sign in the middle is a cosine of a difference. You're subtracting the alpha and the beta. So we can go ahead and say it's going to be cosine of alpha minus beta is the pattern that it's following. So this is following a cosine of an alpha minus beta pattern. And what is the alpha? Alpha is 49. So we can say the alpha is 49 degrees. Minus, what's the beta? 4 degrees. And then we can kind of continue on with that. 49 minus the 4, that should get us 45. And cosine at 45 degrees, if you don't have it memorized yet, 45 degrees, that is a 1 radical 2. What's our cosine ratio? X to r, so 1 to radical 2. And then you can rationalize that, radical 2 over 2. So that would be using the formula in another direction. So they give you the longer cosine alpha, cosine beta, plus sine alpha, sine beta, bringing it back to its shorter form, which would have been cosine of an alpha minus beta, which would also be the same thing as cosine of the 49 minus the 4, and then you can just evaluate that. So final answer, that should simplify to radical 2 over 2. And looking at the next one, same idea. You do need to watch out for the fact that your alphas and your betas are not all the same. So notice we have cosine alpha, cosine beta, but notice it's not the same as this number here. One's negative, one's positive. So here's where you can use your even and odd properties for your trig functions. So we know cosine is an even function. So a negative input is identical to a positive input. So cosine, if you remember the identity from earlier in the chapter, cosine is even. So cosine of a negative angle is identical to cosine of a positive angle. So essentially for cosine, if you see a negative, you can just go ahead and get rid of it. So we'll call this cosine of a 3. So we can go ahead and rewrite this. We'll say cosine 2, we'll leave the 2 the way it is. But cosine of the negative 3, we'll just rewrite it as cosine of 3. Minus, and then notice again our angles don't match. We have a 2 on one of them, but we have a negative 2 on this one. But sine was an odd trig function. So sine of a negative x is identical to sine of a positive x, just multiplied by negative 1 in front, so the negative kind of gets bounced out to the front. So if I bounce the negative out to the front, you're going to get a negative and a negative, so 2 negatives in a row, but that will get our angle to match, sine of 2, and then sine of 3. So now we have matching angles. Now we have a 2 and a 2, not a negative 2, and we have a 3 and a 3, not a negative 3. Simplify a little bit more. The 2 negatives in the middle, you can make that a plus. So we'll say cosine of 2, cosine of 3, plus sine of 2, sine of 3, and that's going to be a plus in the middle, so it's going to be following the cosine of a difference. So this is following a cosine of an alpha minus beta pattern. So cosine of, what's our alpha? That should be the 2. Minus, what's the beta? 3. 2 minus 3 is negative 1. And here we can simplify this again. We can use the even property of cosine. If you have a negative input, that's the same thing as just having a positive input. So the -1, we can just call that +1. So cosine of 1 radian. So that's radians because there's no degree symbol on those, so those are assumed to be radians. And 1 radian is not a special angle, so we can't do a triangle and find the exact value. That's just going to stay cosine of 1 radian. And the next part of the notes, so this is going to be on the idea of cofunction identities. Cofunctions are basically the complementary trig function coming from the complementary side of the triangle, so the other side of the triangle. So you have six trig functions. One of them is sine, and then the other one is cosine. So sine and cosine are said to be cofunctions. And what it means to be a cofunction is you're just working from the complementary angle, the other side of the triangle, to make the same ratio. So for example, if I had a right triangle, and if I said I had an angle theta, and I had my side lengths A, B, and C, if I looked at the cosine ratio from angle theta, or not, sorry, let's do the sine ratio. So if I did the sine ratio from angle theta, then what would we say the sine ratio is? That's going to be opposite versus hypotenuse. So that is a to C ratio. However, what if I wanted to go work from the complementary side of the triangle but still have the same identical ratio? So remember, we're studying identities, so we're trying to keep everything identical. So we want to keep the same identical ratio A to C, but we're going to go to the complementary side of the triangle. So whatever angle theta is over here, for example, if it was 40, then it would have to be 50 for the complement. If it was 30, it would have to be 60. So this is going to be 90 minus theta over here, the complement. So if I wanted to use the complementary angle, 90 minus theta, then which trig function would I want to use here to get the A to C ratio? So you still want to get that A to C ratio, but you're not going to use the sine ratio anymore if you're over here at this angle. If you're at this angle, you would actually use the cosine ratio. So the cosine ratio of that other angle is going to be A to C. So if you go to the complementary angle, then you go to the complementary trig function. So just to do a few more quick examples, and we'll just stick with sine and cosine for the moment. So let's say I had the sine of 30 degrees. But I wanted to write it identical to something using the complementary angle. What's the complement of 30 degrees? Complements add up to be 90, so it's going to be 60. 90 minus 30 is 60. So if I wanted to use the complementary angle, I'm going to have to switch to the complementary trig function, which is cosine. So the sine of 30 degrees is 1/2, and the cosine off of 60 degrees would also be 1/2 if you were to work that out. So these are going to be identical. Let's say I had 40 degrees. So let's say I had the sine at 40 degrees. Let's say I wanted to go to the complementary angle, which would be 50 degrees. 40 plus 50 is 90. Then you're not going to use sine anymore. You're going to use the complementary trig function, cosine. So the co stands for complementary, so the complement of sine. And that's going to hold true for your other trig functions as well. So if you had tangent. So if you had a tangent function, then what is the complementary trig function? It's going to be cotangent. So that is your complement to the tangent function. And if you had secant, then what is the complement to secant? That's going to be cosecant. So again, that is your complementary trig function to secant. So if you had, for example, secant at, let's say, 20 degrees, and let's say I wanted to use the complement to that, so 90 minus the 20. So 90 minus the 20, its complement should be 70. Then we're not going to use secant, we're going to use its complement, cosecant. And then obviously you can use the abbreviations. So the abbreviation for secant is SEC, and then cosecant, and those would be identical to each other. So those are your cofunctions. So up here in the box is just your different definitions. They're given to you in radians, the pi over 2. But that's basically just 90 degrees if you want to think of it as 90 degrees. So if you have complements, pi over 2 minus some angle u, or 90 degrees minus some angle u, then that's going to be its complement, and it kind of works the other way. If you have 90 minus an angle, that's the complement of u. So those are going to be your cofunctions.